So the types of proteins that we have inside these cells will be myosin and actin. And then I was explaining the shape of these proteins. So the thicker proteins will be this myosin, which it has this tail with two subunits that form like a helix, and then you have a hinge that allows the heads, which are these, to move toward the center. So you have heads on this edge of this myosin and on this other edge. And then the tails, they are found here in the middle. So if you magnify one of these myofibrils and then you see the myofilaments, they form this banding pattern. So this is the A band, the dark band, and this is the light band. And then in the A band, you have myosin, and then you have actin. Actin is the thin myofilament, and it has these subunits that are the actin globular proteins. So this is called G-actin. They form a polymer, and this polymer forms a double helix that is held together by this tropomyosin. And then tropomyosin is kept in place by troponin, which is a small protein that has 3 subunits. One of these subunits binds calcium. And when it binds calcium, this tropomyosin moves away from this actin and exposes this actin active site that binds specifically the head, forming a bridge. And there is a physical connection then between actin and myosin during contraction that is, for the most part, temporary. And then after you have this physical contact, actin slides toward the center of the A band, decreasing the length of the I band. And then you will have the 2C discs, which are these, going towards the center of the sarcomere, and then you have contraction. And then after you have contraction, titin is going to basically make these myosin heads to return back into this specific length that you had before contraction. And it does so because this is an elastic filament, titin. So this is how I illustrate this. So we have this metal rod that it helps to secure these devices in this station, computer station. And then let's say this yardstick is one of the myofilaments, and this is one of the myofilaments. So which myofilament will be actin? The yardstick or the rod? Or sorry, or this metal rod, yes. So which one will be actin? Look at the shape. This is myosin and this is actin. So which one will represent actin? This or this?
Yardstick.
Hmm?
So it's the yardstick.
Yes.
Because the one on top is thicker, right?
Mm-hmm. So what part of the myosin then, if this represents myosin, will be this part? Head, tail. This is the head. So then, the way that I represent contraction, let's pretend that I had another rod in here, and this will be actin. Okay? So actin is going to be on this side, and then when you have calcium available, troponin is going to bind calcium and then helps for tropomyosin to move away. Then this actin can interact with the head of myosin. So physical connection between actin and myosin, and then this head is going to swivel the head this myosin is going to swivel the head toward the center, helping to do this. So this is the sliding mechanism. Actin is going to slide over myosin. Any questions? So that's what happens. Myosin is super heavy. So that's then what makes the contraction to happen. And then if you make sections of this part and look at the different components, you will see what happens at every space, or what we have at every space. So this is the eye band. In the eye band, you have only thin filaments, only actin. And then in the A band, or the dark region, it depends on where you make the cut, what you will have. Like if you cut this A band next to the I band, you will have both actin and myosin. So actin is represented in blue color, while myosin is represented in red color. And then if you move toward the center of the A band, which is the H zone, in the H zone you only have the tails of myosin. But you don't see any blue coloring here because you don't have actin. So the outer edge has thin and thick filaments, actin and myosin, same as this part, but as you move towards the middle of the A band, in the H zone, you only will have thick filaments. And this is like the view of sarcomeres in relaxed and contracted states. So when you have a relaxed sarcomere, when you don't have contraction, there is no overlap as much of actin over myosin. So in the H zone, which you have this specific diameter, you only have this myosin, part of the tails and part of the heads. And then when you slide this actin over myosin during contracting state, you see how this part of the H zone become darker. Why? Because now you have actin sliding over myosin. And then your I band becomes shorter. You can see it here. So this one, it was long. And then when you slide actin over myosin, this one becomes short. But there is no change in the diameter of this A band. However, the H zone become shorter. So see here how the H zone, it is wide, and then how it here becomes narrower as actin slides over myosin. Questions? Okay, so now for the physiology of this contraction. So how does these muscle fibers generate electrical signals? In excitable cells like neurons and muscle cells, you have the generation of electrical signals known as action potentials. When the cells are doing a specific function, they generate these action potentials, and when the cells are resting, they have something that is called the resting membrane potential, or RMP. So this RMP in the muscle cells is around minus 90 millivolts, or lowercase m and then capital letter B. So this is a unit of potential energy, which is voltage, and it's a millivolt, so it's 1,000 of a volt. So in this case, that unit. In this case, the cells internally, when they are not doing any activity, they have minus 90 millivolts. And then these cells will have receptors in the plasma membrane that can bind acetylcholine. Acetylcholine is a neurotransmitter that makes the cells to be able to bring in sodium ions. And if you remember, sodium is a positively charged ion, so it's a cation. And then when sodium comes in, these cells will become less negative. So that is going to change the electrical state of the cell. So it's going to become less negative, and the entry of sodium is going to be called influx, sodium influx. So the process of bringing in sodium and making the cells less negative is going to make the cells to reach a threshold in which the cells will make more sodium come in, and then the cells, instead of having minus something millivolts, they will have, they can reach up to plus 10 millivolts. So they become completely positive. And this process actually is called depolarization. And then you have a limit. So you can reach plus 10, plus 15 millivolts, and then you close your sodium channels in the plasma membrane, and then you open the potassium channels. And these are voltage gated channels. So that means like they have a part that closes the channel when the channel is inactive, preventing ions to moving. So then at plus 10, plus 50 millivolts, you close your sodium channels, no more sodium comes in, and then you open your potassium channels. And potassium, since it's more concentrated inside the cells than outside the cells, they will rush potassium ions outside the cells, and the cells will become less positive. So they will return into the resting membrane potential, and this process is called repolarization. In this case, you have efflux of potassium. So here you have it. Repolarization equals potassium efflux. Potassium, just as sodium, is a positively charged ion, so it's a cation. So then you will be losing this potassium, and then you will repolarize yourself. Now, this event initially happens in a space that is called the neuromuscular junction. The neuromuscular junction, it is a synapse. So it is a place of communication between a neuron and a muscle cell. That's why it's called neuromuscular junction. And then you have the release then of this acetylcholine by the neurons. The membrane of the cells, the muscle cells pick up this acetylcholine. You open these sodium channels, you depolarize the cells, and then your cells reach this positive state, and then you repolarize them. And that cycle starts over again, and then you have sliding of this actin over myosin. And as this happens, this action potential propagates or migrates within this sarcolemma, within the plasma membrane of the cells. And then it will go internally into the T tubules. So the electrical signal goes by through these structures. And then when you have these thin and thick filaments binding, the physical connection, the bridging, you have the contraction, you have shortening of your sarcomeres. And then again, I told you this before, but you have to have calcium available if that is going to happen, because troponin won't move away from tropomyosin and if you don't have calcium. And then you have within the heads of myosin an enzyme that is called ATPase, and that ATPase will bind ATP, and it will break it down into adenosine diphosphate. So you will lose a phosphate group, and then you will have release of this bridge between actin and myosin. So while calcium is necessary for contraction, ATP is necessary for relaxation. So sources of calcium for contraction of the muscle cells, it is intracellular calcium that we have in the sarcoplasmic reticulum, but also extracellular calcium, so calcium from outside of the cells. So calcium can come in through channels that we have in the plasma membrane, and once your cell depolarizes at the T tubule, you have on the sides the cisterna of the sarcoplasmic reticulum that has voltage gated calcium channels. So when you have depolarization, you open these voltage gated calcium channels from these deposits of calcium, and then calcium is released. You have contraction, sliding of myosin over actin, and then once you have ATP broken down by the head of myosin and relaxation, whatever calcium is left over, it will go first into the sarcoplasmic reticulum to be stored back again for the next cycle of contraction and relaxation. And then they just try to illustrate with this image in your book the sliding mechanism. So if your hands will be actin and myosin, myofilaments, and then these knuckle heads will be the C disc, and then you have a specific, during relaxation, if you have a specific overlap of actin over myosin, you can call whatever fingers actin or myosin from your left hand or the right hand, but the point is that you have this sliding, and then you have shortening of your sarcomere. If this space between your knuckleheads will be the sarcomere, that decreases the space. So that's what happened. And relaxation, contraction, relaxation, always sliding. Okay, that's happening for as long as you live. Let me explain that. So this is the illustration for the different events. So starting with the resting membrane potential, or RMP, what makes it to be? So here we have your plasma membrane, your sarcolemma. This is the phospholipid bilayer with the phosphate heads facing externally and the fatty acids facing internally, the fatty acid tails. Embedded within this plasma membrane, you have some channels of potassium that are called leaky channels. In this case, these leaky channels are always open. They don't have a gate. So in theory, well, actually in practice, the potassium exits the cell constantly through these leaky channels. So the space here above, this area, the one is shown in blue color, that's the ECF, extracellular fluid, or extracellular compartment. And then this space below, shown in yellow, is the cytosol. So because you have leaky channels, you're constantly having potassium exiting the cells, but it returns by a concentration gradient. Remember that in physiology, items move from more to less, simple diffusion, but we have this exchange between the extracellular fluid and the cytosol of potassium ions. And then you have something that's called electrochemical gradient. So by having negative charges inside your cytosol, positive ions like potassium are attracted to be inside the cells. Now, these negative charges are shown in here by this minus sign, and the positive charges that are found outside the cells is shown by this plus sign. The most concentrated ion outside the cells is sodium. Positive ion is sodium. And then the most concentrated negative ion is chloride. And then inside the cells, the most concentrated ion, it is potassium. So then, based on concentration gradient, because you have more potassium here inside the cells than out, you have more exit of potassium through these leaky channels. And then you also have more potassium channels that are leaky than any other type of channels. But then you will have return of these potassium channels back into the cells because you have attraction of this potassium, which is positively charged. It's a cation by the negative charges that we have inside the cells, which are made by the different amino acids that we have that has a negative charge in the proteins that we have, and as well because we have a lot of phosphate groups within some of these molecules in the cytoplasm, and also the actual phosphate groups that we have within the nucleic acids, RNA and DNA. So the concentration gradient then is slightly stronger, so a small force favors the movement of potassium into the extracellular fluid. And the electrical gradient favors the potassium moving into the cytosol. So that's an electrochemical gradient. So then you can see here now the combination of potassium and sodium. Sodium represents these purple dots, and potassium these blue dots. So again, as I told you before, sodium is more concentrated outside the cells than in, and potassium more in than out. So direction of diffusion for potassium is favored in this direction, while sodium is favored in this direction. And then we also have some of these sodium leaky channels, which are represented here in purple color, just to represent that these purple dots will move in this direction, while potassium in this direction. And because we have more leaky channels for potassium than sodium, you expect that less sodium comes in and more potassium comes out, and that will keep the cells to have a minus 90 millivolts. Now the phases of action potential. So we have depolarization and repolarization. So in resting state, the voltage-gated channels for both sodium and potassium are closed. And that can be traced here in this graph. In the graph, in the y-axis, it shows you the millivolts from minus 90 up to plus 30. And you have here 0 millivolts. So if you were measuring the internal electrical activity with an oscilloscope, and you will have a trace in the monitor, in resting membrane potential, you will have this line at minus 90, and then when you open your sodium channels, when you stimulate these voltage-gated channels to open because you have, for instance, acetylcholine available, then because you have more sodium out than in, sodium will rush in, and then from minus 90, you will go to less negative, and then you can reach positive charges. So this is depolarization. And then when you reach the peak of depolarization, you close your sodium channels, and now you open your potassium channels. Potassium rushes out, and that returns the polarity of the cell to resting membrane potential. That will lead to gradual decrease of this voltage to minus 90 back again. Sometimes it can go a little bit more than 90, and that is called hyperpolarization. And this happens in 2 milliseconds, very fast. 1 second has 1,000 milliseconds. So if it happens in 2 milliseconds, you can expect in 1 second, one cell to be capable, if it has the right conditions, to have 500 action potentials happening in 1 second. And that's what basically makes the muscles to contract, but also that happens in excitable cells like the neurons. The neurons work with the same principle. And then we have a bunch of action potentials happening in our body every time. And then you may be working out, maybe listening to a lecture while you're working out. Basically, that keeps all your excitable cells so busy that you spend a lot of energy. And then you learn because your neurons modify the connections and they become stronger. So these are the structures of the neuromuscular junction. So this is the muscle fiber, the cell, and it is connected by this motor neuron. The neurons that makes our muscle cells to move are called motor neuron, motor for movement. And abbreviation of neuromuscular junction is NMJ. So if you magnify this area where this motor neuron is located, this is what you will see. So this part of this motor neuron is what is called the axon terminal. We will see the details of the axons and the neurons in general in the following chapters. But this is like a dilation of this part of the axon. This is called the axon terminal. And internally, these axon terminals has little pouches filled with acetylcholine molecules. The abbreviation for acetylcholine is ACH. And then you have within these axon terminals voltage-gated calcium channels. So when this neuron generates an action potential and travels to these axon terminals, you change the voltage here, calcium rushes in, and then this vesicle fuses into this membrane of the axon terminal, then release the acetylcholine, and the acetylcholine by diffusion moves from the neuron into the muscle cells, passing through a physical space that it is called the synaptic cleft. And then we have receptors within this area where we have the channels. And then when acetylcholine binds, then these receptors activate the opening of these channels so that sodium rushes in, and then this cell depolarizes. Now, this specific area where you have these channels and these receptors is called the motor end plate of this neuron. So then if you see a little bit more than just this space in the motor end plate, So this will be what happens. So you release acetylcholine, then the receptor receives acetylcholine, you open the channels, sodium uracil, and then this plasma membrane, the motor end plate, become depolarized. And then that depolarization will propagate, will go into other areas. So this is a sarcolemma. It will have more sodium channels, more sodium channels open, sodium rushes in. This area becomes depolarized, and then this one starts to repolarize, and this one starts to repolarize, and then you will have the propagation along the surface of the cell in the sarcolemma, but also look how this green arrow that represents the migration of the action potential, how it bends over to go through this T tubule, which is the extension of the plasma membrane, so that the depolarization goes deep into the cell, and then you have these sodium channels that keeps this action potential to propagate, and then here you have the terminal cisternae of the sarcoplasmic reticulum that has these voltage-gated calcium channels that opens when this area depolarizes, and then inside this cisterna you have your bank of calcium. So calcium is released, and then this calcium now is free to attach into the troponin, so that troponin can let go tropomyosin let go actin, and actin can now interact with myosin. So that after that happened, then the calcium channels will close after you have stored back calcium, and then this is at rest. So when your calcium channels are closed, troponin is bound to tropomyosin, which is bound to actin, and myosin cannot interact with actin because the actin active site is not available. But then calcium becomes available, then troponin binds calcium, and this tropomyosin slides over, and then you have this actin active site exposed so that the head of the myosin can bind to there. So I compare this calcium as to when someone is initially dating, it's young, they send you with a chaperone, and the chaperone is there all the time so you don't kiss the other person, right? And then what would you do if you are in the park for the chaperone to just go away and then tell the parents, like, well, you were kissing your date? If the truck of the ice cream comes, you give $5 to the chaperone and say, let's go and buy some ice cream. And then he goes and buys some ice cream, and that's your moment. So ice cream will be the calcium. So calcium binds to troponin. Troponin let go tropomyosin, and then you can have interaction between actin and myosin. And again, once contraction finishes, you store calcium again, and then troponin binds again to tropomyosin, which binds to actin active sites. Okay, so how does the cross-bridge cycle drive muscular contraction? Well, you have a sequence of events like breaking down after you have the sliding of actin over myosin, the breaking down of ATP in the myosin head which actually helps to cock the head, preparing it for binding. So then it is true that you will have, of course, physical interaction initially when you contract actin over myosin, and then you have ATP that is available nearby, hopefully, nearby the head of myosin. And then once you have this ATP hydrolysis, you will release that contact between actin and myosin, letting the head to let go, but be ready to prepare for the next set of contraction once you have calcium available. And then you will have, when you have this actin and myosin cross bridge, something that is called a power stroke, which you have when phosphate detaches from myosin, and myosin will pull actin towards the center of the sarcomere, and then you release your ADP. And then this cycle will be able to help us to generate a specific force that it is necessary for developing tension. So here is the complete cycle then. Release of acetylcholine, depolarization of the motor end plate, propagation of the action potential through the sarcolemma surface, and then deep into the T-tubule, opening of calcium channels in the sarcoplasmic reticulum, release of calcium, calcium binding to troponin, troponin helping for the removal of tropomyosin that is covering the actin binding sites or actin active sites. Then you will have ATP hydrolysis that cocks the head of myosin. Myosin now can interact with actin, forming a cross bridge. And then when phosphate is released, the head of the myosin let go of actin, and then you prepare for the next cycle. So this is like a better view now looking at what happened with the sarcomere. The middle actually of the sarcomere is the M band in the middle of the H band. So this contraction that happens in the power stroke when you cock the head of the myosin is going to bring, of course, actin closer to the M line. And then after that happens, you will have this period where the head of the myosin is going to be aligned, and then it's going to bring it closer to the M line, and that will decrease the size of the H band in the middle of the A band. So that's the cross-bridge cycle events. So where does this energy come from? Well, it comes from creatine phosphate that provides ATP. And also we have glucose available and glycogen that through glycolysis can generate ATP anaerobically, and also at the same time you form lactic acid or lactate that can make your muscles to get sore after you run out of nutrients. And then you have within these cells as well oxidative phosphorylation that produces ATP in the mitochondria. And the muscle fibers will depend on the pathways for ATP depending on the activity and duration of the physical activity. It is well known that when people do exercise and it's very strenuous, ultimately they run out of ATP, and that can lead to cramps. Why is this? Because, of course, you don't have more nutrients to generate your ATP, and ATP is necessary for letting go the cross bridge between myosin and actin. And once the person gets ATP, like maybe if it's a marathon runner, we might have like this energy drink. Well, not an energy drink itself, but one of these drinks with electrolytes that has sugar in it. That will help for the person to get more energy. And then, depending on the muscle fibers, is what metabolic pathways these fibers prefer. So we have immediate energy sources. Then for contraction of the muscles, like we have creatine plus ATP that forms this creatine phosphate. So then when you dysphosphorylate this creatine, you have ATP available from your stored ATP in your muscle cells. And if not, if you run out of glycogen from your muscle cells, you can have glucose coming from your blood vessels that ultimately both of them feed into the glycolytic cycle, which is an anaerobic pathway, and then you generate pyruvate. And if you don't have oxygen, you will generate lactic acid. But if you have oxygen, this pyruvate will enter into the mitochondria as acetyl-CoA to feed into the Krebs cycle, and then you form most of the ATP from oxidative phosphorylation. So oxidative phosphorylation is a major source of energy, not only for muscle cells, but for other cells. Glycolysis only gives you 2 ATP, so it's like not very good. But this one is the ultimate goal, that as long as you have oxygen, and of course a source of energy, you have ATP for contraction. Something that naturally happens after we die, it is the temporary contraction of the muscles that is called rigor mortis. Rigor mortis occurs because you will have the cross bridges of actin over myosin that you won't let go temporarily because you don't have ATP. I mean, if you die, how are you going to generate ATP? So that your muscles will be stiff. The time varies, but it can be up to 6 hours of rigor mortis. And then after that time, your muscles become softened. And this will be because naturally we have enzymes that will break down not only these cross bridges, but the cells themselves. So we have autolysis. So our cells will start decaying. Okay? But rigor mortis, in a way, can be used as well to determine the time of death, if it's catch, of course, earlier. And then I told you before about muscle cramps. So muscle cramps are involuntary sustained muscular contractions because you have excessive stimulation, you might have dehydration, electrolyte imbalance, or fatigue. And then you have this prolonged cross-bridge cycling, and you have elevated calcium in the muscle cells that disrupts the physiology that we speak about. And then again, you have depletion of ATP, which leads to sustained contraction of the muscles. Okay, so now let's look at tension. So tension varies depending on the muscle fiber, and this tension has some phases, like we have a twitch contraction phase that is latent, another one is contraction, another one that is relaxation. And these phases will be related to the activity of the muscle fibers and the type of muscle fibers. So the more that you use your muscles, you stimulate more contraction, of course, and that can lead to some events that recruits more motor fibers, and then that increases the force. So now we have a length tension relationship. So the optimal sarcomere length will produce the maximum tension. There is a specific amount of actin and myosin head overlap that can produce this maximum tension. If you don't fully contract up to this length, the muscles, you don't expect to have more tension or more force. And we have some contraction types, like we have something that's called isotonic, which has two variations, concentric and eccentric, and we have isometric. In isometric, you have the same length of the muscle fibers, and the tension increases. And in isotonic, you don't have you have more tension, but the tension can be going towards the center of the muscle, which is concentric, or eccentric away from the center of the muscle. So when you recruit more motor units, you will have more stimulation of your muscle. That will lead to increased tension. And then you reach a peak. Not because you supercontract your muscle, you can recruit more motor fibers. I mean, the motor neurons. So a motor neuron, it is a neuron that can stimulate muscle fibers individually or as a group. We have large motor neurons and small motor neurons. Depending on the muscles is which type you will have. But you have a finite number of nerves. So then, when you stimulate high frequency your muscle, you stimulate the formation of, the function of more motor units that increases your tension. And then you reach a peak, and then you will have to return to this low tension during relaxation, and then you can have something that is called a muscle twitch with latent contraction and relaxation periods. So latent is the potential that you have to generate that tension, of course, that's why it's called latent. And then you have the contraction itself, and then you have the relaxation. And then you can modulate your tension by recruiting less motor units. Sometimes you can train that to happen. Sometimes that training never happens. And I mean, sometimes people is naturally strong, and then when they tap your shoulder, they believe like they tap you very gently, but you just say, oh, where is my lung? Because they're very strong. And you can tell, guys, sometimes in the brakes of cars. There are some people that, I mean, they can have the same a new car, or they can put new brakes in their car at the same time as other ones. And people sometimes is very gentle when they apply the brakes to their car, and they don't worn out the brakes as much as the other person in the same period of time and with the same use. So anyway, but again, this is something related to modulation. Some people can be trained to modulate the tension. It's like when you're learning to play an instrument. So you know, for instance, when you're playing a piano, like not to tap so much in the keys. So here is then the periods of tension. here is the percentage of tension, and the stimulus starts from time 0 up to 40 milliseconds. Latent, it is when the action potential spreads through the sarcolemma. You still haven't recruited any motor units in here, but then after 2 milliseconds, when you have the stimulus, you start building more tension as you increase the cross-bridge cycling, and then you reach your peak. So this is the contraction periods between 2 to 20 milliseconds, and then you reach your peak, and then you have the relaxation period that typically is longer than the contraction period. So in here it takes 18 milliseconds to contract, while in here it takes 20 milliseconds to relax. Why? Because you have to have time to pump back the calcium into the sarcoplasmic reticulum, and that's not immediate. Calcium is necessary, of course, for many physiological processes. We're talking about right now of a skeletal muscle, but when it comes to survival, let's say that you have hypocalcemia and you have your storage of calcium in your bones. Well, the first organ that is going to reclaim calcium is going to be the heart. I mean, who cares if you're contracting your skeletal muscles? But the heart has to be 24/7. So that's when calcium is very important, and that's why you take more time in general, no matter if it's a skeletal muscle, to store them back. Now for tetanus, which is a sustained contraction, we have this tetanus caused by rapid and repeated stimuli in your muscle fibers, like when you're doing exercise, for instance. And then we have two types of tetanus, one that is called unfused or incomplete, and another one that is called fused or complete. So in unfused or incomplete, you have around 50 impulses per second before you have full relaxation. So this stimuli, it makes your cells to have sustained contractions with partial relaxation, and you develop less tension. And then when you have a complete or fused tetanus. So this type of infused tetanus happens in muscles to have a smooth graded muscular contraction when you are making moderate activity. So you don't want to fatigue your muscles as much. So that's like most of the type of tetanus that someone can develop. Now, in someone who's having high frequency stimulation, like between 80 to 100 impulses per second, in this case, you will have less time for restoring calcium in your storages in your sarcoplasmic reticulum. That will prevent relaxation from happening, and calcium levels, since they're going to be available in the cytoplasm, will still binding to troponin, and that will lead to sustained contraction that is going to make having, of course, a peak of muscle tension. You will have certain fluctuations but at the beginning, but generally, as you continue with this type of stimulation, you won't have fluctuations, so you won't have relaxation. That will give you the maximum force before someone has fatigue. So this is what happens between both of them. So this is a trace of unfused tetanus versus fused tetanus. So this y-axis showing you your tension from 0 to 100%, and then in here you have the time in milliseconds. So the space in time between stimuli in the infused is greater. So you have more distant stimuli than here. Here is more frequent. So this is 50 times per second versus 80 to 100 times. So in here you have contraction, relaxation in a way, and then you reach your maximum with time. A little bit more gradual than in here. So in here, within very few milliseconds, you reach your maximal tension. You don't have period of relaxation because you have a lot of calcium available. So that reaches your maximal tension very quick, more likely to get fatigued. This is not so much activity, this is a lot of activity. And then the tension itself depends on the length of the sarcomere. So you have an optimal length in which you have the maximum overlap of myosin over actin. So that produces 100% tension. The minimal, it's not going to give you, like if you don't slide completely your actin over myosin, it's not going to give you as much tension. And then you have sometimes, for instance, in the wrist, when you have your wrist flex, when the sarcomeres are too short, like if this was kind of showing you this contraction, you will have excessive filament overlap that reduces the tension. And then, like if you have the wrist hyperextended, mimicking your sarcomeres, that's when you have 90% maximum because you have reduced filament overlap that lowers the tension. So there is a curve that shows you that the tension optimal length can fall when sarcomeres are too short or too stretched. And this can be illustrated like this. So here you have this muscle, which is in the posterior area, in the anterior compartment of this is an extensor. So let's call this situation when you have your wrist extended at natural length, your maximal tension. So in this case, you have this actin and myosin producing this maximal tension when you have contraction. And then that can be traced as percentage in here and length in here. So the length of your sarcomere has to be between 60 to 180 micrometers, let's say. And then when your muscle of your forearm, it is flexed because your wrist is flexed, then you have an overly shortened sarcomere. That leads to 85% of the maximal tension. And then that's because you will have the myosin heads in here, and then you have the tails in here, which cannot interact with actin. So in here we don't have the maximum tension. And similarly, if you hyperextend your muscle becomes stretched. So in this case, you pull away actin, increasing the length of your sarcomere. You pull away the heads of actin that might be here, the heads of myosin that are in here that cannot interact with myosin. And you have a little bit more of tension than in this case, but it's not as much as this. And this is like an isotonic condition when you have your maximum tension. Any questions? Now, skeletal muscle fibers can be subdivided into different types depending on the metabolic activity. So we have slow fibers, or type 1, that are slowly oxidative. These fibers, they use aerobic metabolism, and they are resistant to fatigue because you have oxygen available. These fibers, if you look them under the microscope, they look darker because they have high myoglobin, which is this protein that helps for the metabolism of muscle. And then you have a lot of mitochondria. So where do we have these type 1 fibers? We have it in the muscles of our back, in the soleus muscles that helps for carrying the weight of our body in a way. And then we have type 2A fibers, which are fast oxidative. These ones are intermediate in resistance and fatigue resistance and metabolism, so they can have aerobic and anaerobic metabolism. And they look in appearance between type 1 and type 2B fibers, which are the fast glycolytic fibers. So we have them in muscles that requires power and endurance, like our leg muscles, and some upper limb muscles, like the biceps. Fast glycolytic fibers, or type 2B or 2X, these are fatigue non-resistant fibers. They undergo anaerobic metabolism, and we have it in areas of the body that requires rapid and powerful contractions, like our eye muscles and upper limb muscles. So then these muscle fibers are more easily fatigued, the 2B than the 2A or the 1. So this is how these different fibers look like. We have here type 1 and type 2. So these are darker than these ones. Now, how does these motor neurons control our muscle fibers? So we have the spinal nerves coming from the spinal cords that extends through the pathways of the different tissues in our body, reaching the skeletal muscles. And then depending on the motor neuron is how many fibers they're going to stimulate. So we have motor units that control different groups of muscles that allows precise movements or control the muscle force. So the ones that they are small motor units, like if they have parallel interaction, like one muscle fiber innervated by one motor neuron, you have more control. And in this case, we will have fine movements. For instance, we have a lot of nice coordination within the fingertips and also within our eyes because we have smaller motor units. And then in our muscles of the back, the legs, where of course you need to have certain coordination, but it's not as important as for the fingers. You have larger motor neurons. That means like one motor neuron can control several muscle fibers at once. And then in this case, you generate more tension rather than controlling movement. So then the recruitment happens in the following way. So first you start with smaller motor units. If you have muscle where you have both small and larger motor units, you start basically recruiting first the one with less number of units, less number of fibers, and you will have low force first, and this help you just in case that you're not doing something that demands a lot of force, you will have an endurance task. And then later on, you will recruit the larger motor units that are fast glycolytic motor units as the force demand increase. And then you enable graded control of the muscle tension. So something that happens when people learn perhaps to paint or play an instrument is that they start training these motor units, and then they develop finer movements. So here we have a cross-section of the spinal cord. We will see later details of that in the following chapters. But this is the anterior horns of the spinal cord. And here we have two motor neurons. Motor neuron 1 in red color, motor neuron 2 in blue color. So, which one has the small motor units? Axon 1 or neuron 1 or neuron 2? The small motor unit. Which is the smaller motor unit? 1 or 2? 1, because it controls 3 muscle fibers. And this one controls 5 muscle fibers. And this is an example. So then, when you are going to perform contraction of a particular muscle that has a mixture of these motor units, you will recruit first the smaller ones, and then you continue with the larger ones. The differences between the contraction of the muscles. So isotonic concentric, the muscle shortened while producing force, like lifting a dumbbell. That's isotonic contraction, concentric. In eccentric, your muscle lengthens while maintaining the force. It's like the opposite of lifting the dumbbell, lowering the dumbbell. And then in isometric, your muscle length remains the same while the tension increases, like holding the dumbbell steady without moving it. And even without the dumbbell, if you extend your arm or in your forearm, if you contract your biceps without doing this, you can do so. You can show off your muscles, I guess, if you want. You just contract and you feel a little bit more stiff. That's isometric. You don't decrease the length. You just increase the tension. I don't know if I said it the other way for isotonic before, but in isometric, the length remains the same while the tension increases. And then in isotonic, the tone remains the same without change the length. You shorten the length. All of these muscle types, all of these contraction types allow you to perform different tasks, including movement, control, and stabilization. So, okay, so let me give you an example. I think with this. I have here a light object, right? And then, if I carry this light object, like here with my palm, well, I can be doing just isometric contraction. because I don't require a lot of force. But then, instead of this, now I put this in my palm. Guess which one that I have to do? And I'm holding it with this because it's heavy. So I have to do isometric or isotonic. And it is concentric or eccentric. Because if I don't do it, if I just try to keep it like if it was this, guess what is going to happen? I'm going to damage my arm. So say quickly which one it is. Isotonic, what? Mm-hmm. So that's kind of natural. Sometimes we don't think about it, but it would be crazy. Like if someone gives me a light object to carry, and I will be like, oh yeah, I have to carry it so strongly. I will be like, yeah, you're ridiculous. So that's the type of contractions that we have.